Hello. Today we will be talking about enthalpy changes. We'll be talking about the first equation, mc delta T, endothermic and exothermic reactions, Hess's law, and solving problems with bond enthalpy. Okay, so to start off with this equation, M stands for mass in grams. C is for specific heat capacity. And change in T is difference in temperature. So final temperature minus initial temperature. Okay, and so why do we use this equation? We use this equation to see the difference in heat, which results from a specific chemical reaction. So let's say we have a beaker and we have a solution of water. We have some water in it. And we're going to have some reaction happening here. We're adding something A plus B. And it's taking place within this medium of water. So A and B is going to be called the system. So the system is basically whatever is reacting, which is your reactant A and reactant B. These are going to be considered to be our system. And so if this is endothermic, this system will be taking heat from the surroundings, which is over here. So the water is going to lose heat and it's going to go to the system. Whereas if it was exothermic, the system would be releasing heat out to the medium. So the heat in the water will increase and the heat of the system will decrease. And that is what is meant by exo and endothermic reactions. An endothermic reaction will be absorbing heat and exothermic will be releasing heat. So that's why we have the minus sign over here, because when the system is being endothermic, water is losing heat, so that's why it's negative. And if the system, which is the reaction, remember, is being exothermic, then it will be releasing heat and the water will be gaining heat. So that is why the negative is here, because the system is the opposite of the surroundings. And what we get when we calculate Q, positive Q, is what we get, what's going on in the surroundings. Whereas we want negative Q because we want to know what's happening in the system. So, basically, mass is going to be in grams, specific heat capacity. Specific heat capacity is the change, this is the amount of energy that you need to change the temperature of the medium by 1 degree. And it doesn't matter about the volume or anything like that. It's always the same. For example, for water, it's 4.18, and then the unit. The unit is kind of long. And temperature is in degrees Celsius. And Q, you'll probably get it in joules, and you might need to convert it to kilojoules or vice versa. Okay, now moving on to endo and exothermic reactions. Here's the energy diagrams. So first, can you see if you can identify this as exo or endothermic? So we're going to start off by labeling that here are our reactants, here are our products. Same goes for here, reactants, products. So what's happening over here is our reactants are up here. We have our activation energy, which is this, EA, and then we're going back down here to the products. So in total, our reactants are losing some energy, which is going down to the products. This tells us that the reaction is exothermic, because we are releasing heat, which is what exo means. So if we want to label this for some details, we have our change in enthalpy. Over here we have our activation energy. That's about it. Oh, and also, over here, we can see that our reactants are less stable than the products, and the products are at a lower energy level, which means they are more stable. Now, let's contrast that with our endothermic diagram. So if that one was exo, this one must be endothermic, which means they're absorbing heat. And we can see this since we have a positive enthalpy change, and as usual, we still have our activation energy over here, which doesn't really have anything to do with this. So I'm going to erase that. Okay, so our enthalpy change is positive, which is why it is endothermic. And the reactants are more stable than the products, which are less stable because they're at higher energy. When you're at higher energy, you're less stable, more excited. Yeah, so that's endothermic. So in exothermic reactions, our change in enthalpy is going to be negative, and in endothermic reactions, our change in enthalpy is going to be positive because we're taking energy, and here we're releasing it. Okay, now Hess's law. So basically, Hess's law is like if you're driving in a car, so you're in a car and you're trying to go somewhere, and you realize this route is blocked by traffic. So you're like, okay, I'll take a bit longer road, but I'll still get to the same place. This is exactly what Hess's law is. You're getting the same result, but you're going through a lot more steps, and it might be a little more difficult, but you're still getting there anyways. So basically, you would have a few equations, and they get you to the final equation. So over here, I wrote x plus y, let's say, gives us a, and then x plus z gives us b. And we're looking to get a plus b, or something like that. And so basically what's going on here is we're using these two equations to help us get to the final one. And that's just what Hess's law is all about. It's about taking another route to get to the same destination. Okay, now I'm going to solve a bond enthalpy problem, which bond enthalpy is just the average, well, you can say average bond enthalpy. It's the amount of energy that you need to break a single bond. So basically, if we have Cl2 is Cl connected to a Cl, if we want to draw it out. And that's all it is. So the bond enthalpy of Cl2 would be to break this bond, so we get Cl plus Cl, basically. So over here, we have a bond enthalpy problem, and it tells us to find the enthalpy of formation of water. So what we have to do is look at the equation, which is over here, and we're just going to use the formula, which is standard, just memorize it. The sum of all bonds broken minus the sum of the bonds that are formed. And that is the formula that gives you the answer. So what we're going to do here is look at our reactants first, which are going to be the bonds that are broken. But first, we have to remember that the enthalpy of formation is forming 1 mole of the product. So they might try to trick you in instances like this in IB. So I'm going to rewrite the formula first and make sure that it's 1 mole. So that means I have to divide this whole reaction by 2. What we're going to get is this. And that is the real formula that we're going to be dealing with over here. So let's start by drawing all the reactants out. Starting off with 1 hydrogen plus O2 minus, this is going to be the bonds that are broken with our reactants. And then we're building bonds for the product, which is going to be 1H2O. 1H2O. Now, I'm going to sub in some... Wait, let's see first what bonds we're breaking. We're breaking this bond, we're breaking this bond, and we are putting together these two bonds. So, let's start with 1HH plus half, don't forget your coefficients over here, half O double bond O minus 1, 2 OH bonds. So basically we're counting all the bonds and we're just replacing them with their enthalpies. Okay, so it's time to sub in. 1 times 436, which is our value up here. Then we're gonna add half of O double O, which is 498. 498 minus, don't forget your brackets, can't get confused. 2 OH, so 2463. 2463. Okay, I'll pull up our calculator out here. Oops. Okay, so we're gonna have 436 plus, oops, I'm gonna do half. 0.5 times 498. 249, okay, plus 436. Okay, then we have 2 times 463. So we're gonna have this answer minus this answer. We're gonna get 241 kilojoules per mole, sorry. And that is gonna be our enthalpy of formation of water. I hope this video helped, and I hope you enjoyed.